All right, guys, so what we're doing today is inverses. You can pull it shut. I'm assuming chicken patty for lunch. Don't want baked ham. But what we're looking at today is inverses. Now, we did talk briefly about this yesterday in that we noticed that when we multiply two matrices together, if they're square matrices, that's one way we can guarantee that we can multiply it in both directions. Not always. There are some that work the other way around. But if we multiply two matrices together, say A times B, let me write, times B, and we also did B times A, we notice that these are not going to be the same, that we're not going to get the same matrix. Now, the only way that we can actually get the same matrix is either A, one of these two is the identity matrix, or B, if they are inverses. Because if two matrices are inverses, then we'll actually get the same matrix back out. And ironically, that matrix that we get is the identity. So we can say two matrices are inverses if A times B is equal to B times A, which is equal to the identity. And for us, a matrix, the identity matrix for a 2 by 2 looks like this here. Our diagonal of 1s and everything else is 0. For most functions, the identity matrix, or kind of the main one, is y equals x, the equation of a line. If we think of inverses, our f of g of x is equal to g of f of x is equal to x. That's how we kind of identified with functions if they were inverses. But we don't really need that at this point. We're just looking at identity for matrices. So we just need to multiply the two together. So we can do 3, 7, 2, 5. For A, multiplied by 5, negative 2, negative 7, 3. Now we'll do the first one here by hand, and then we can do the second one in the calculator to see how they both work. So we multiply the first one. Over, down, first row, first column. So we have 3 times 5, which is 15. 2 times negative 7 is negative 14. So we could put plus negative 14 or minus 14 would be the same thing. So we normally add each one, but because the 14 is negative, we can say minus 14. Then we'll do the same thing, first row, second column, which is going to give us 3 times negative 2, which is negative 6. 2 times 3 is plus 6. Well, so far it's looking good. Then we can move on to the next one. Second row, first column, 7 times 5 is 35. Plus 5 times negative 7 is negative 35. Well, I think this is still working out well. And our last one, second row, second column, 7 times negative 2 is negative 14. 5 times 3 is going to be plus 15. And if we combine like terms, 15 minus 14 is 1. Negative 6 plus 6 is 0. 35 minus 35 is 0. And lastly, negative 14 plus 15 is 1. So A times B did indeed give us the identity matrix. And we can go the other direction, B times A. And especially if we plug this in, we're going to get, we should get the identity matrix back out. So we can go second matrix over to edit. So we have a 2 by 2, 3, 2, 7, 5. 3, 2, 7, 5. We go second quit, second matrix over to matrix B, which is a 2 by 2. 5, negative 2, negative 7, 3. 5, 7, 3. Second quit. And we could do the one we just did, matrix A times matrix B. Now we don't have to put a multiplication. We don't have to say A times B, because the calculator understands if I put the two next to each other like I just did, that we're saying we want to multiply. We get the identity. Matrix B times second matrix A is also the identity matrix. Therefore, these two matrices are inverses. They're indeed inverses of each other. Any questions on this here? I don't think we need to go into a whole lot of detail of how to tell if two matrices are inverses. Multiply them together. Hey, they're inverses. Well, the other way to do it is I could pick one of them. I can say matrix A and find its inverse. So if I find the inverse of matrix A and it is indeed the same as matrix B, then they are inverses. So we're going to find the inverse of matrix A. Now, in Algebra 2, we went over a way because there was a set formula, and we will go over the formula for how to find the inverse. But we're going to do it a little bit different because there is another way to actually find the inverse. And part of the reason we didn't cover it in Algebra 2 is because we didn't cover row augmentation or row manipulations. So since we didn't do the row augmentation like we did the other day with getting the row epsilon form or reduced row epsilon form, we can actually use it to find the inverse. So what we do is we set it up like this here. We put the matrix that we are given on the left, so our 2, 9, 1, 5. We put a bar and then put the identity on the right. Questions on this so far? Now what the goal is to get, let's get a highlighter. I want a crayon. Highlighter. This side of the matrix to look like this. Well, apparently I'm going to write in a highlighter both ways. We want to get the left side of this equation to be the identity matrix. So we're wanting to turn the 2, 9, 1, 5 into the identity matrix. And if we get it into 1, 0, 0, 1, our identity matrix, the right-hand side will be its inverse. So we're manipulating this side into becoming 1, 0, 0, 1, and whatever we get over here will be its inverse. Now that seems a little weird in how that's going to work. Doesn't quite make sense, but it'll make sense as we do this here. Well, if we want this first spot here to be a 1, well, this one's already a 1, yes? So one thing we could do, kind of writing our we can just flip rows 1 and 2, so I can make the first one be a 1. Okay, and we've done this before, because this is now 1, 5. This is now 2, 9. We comfortable with this here? Yes. But anything that I do to the left-hand side, I have to also do to the right-hand side. So since I switched rows 1 and 2, I had to switch rows 1 and 2. Well, we need this 2 here to be a 0. Yes? So what do I need to multiply the 1 in the first column, first row by to get it to be 2? Well, we multiply it by -2 times row 1 plus row 2 and apply it to row 2. Because we're going to multiply everything in row 1 by -2 and then add it to row 2. So if we do that multiplication off to the side, 1 times -2 is, well, -2. -2 times 5 is -10. Bar. We've got to do it to all of them. So -2 times 0 is 0. -2 times 1 is -2. So I apply it to every number in that row on the left and right side of that bar. Now we're adding it to row 2, so we have 2, 9, bar, 2, 9, bar, 1, 0. And we're adding them together. Okay. So, -2 plus 2 is, well, 0, like we wanted. -10 plus 9 is -1, bar. 0 plus 1 is 1. -2 plus 0 is -2. Now the first row, 1, 5, 0, 1 stays the same. Now the second one is going to become 0, -1, 1, -2. Okay. Well, we got 0 in the second row, first column, yes? Because that's what we wanted. We've almost got the 1 in the second place, but we don't need it negative. We need it positive, but we can deal with that later. And the reason I say that is because, well, we need this 5 to be a 0. So that means that we can multiply 5 by row 2 and add it to row 1. I'm putting in place of row 1. So I'm not changing the sign because if we multiply row 2 by 5, well, we would have 0, -5, 5, -10. The 5 is already negative because of the -1, so we don't have to do a whole lot to it. I put 0 because in the first row is 1, 5, bar, 0, 1. And we're going to add them together. Well, 0 plus 1 is 1. -5 plus 5 is 0. Bar. 5 plus 0 is 5. -10 plus 1 is -9. So now our new top row is 1, 0, bar, 5, -9. And our second row is this here. Now, looking at this here, we can see that we're almost there. We almost have the left-hand side as 1, 0, 0, 1. We just need to change the negative 1 to a positive 1. So we're just going to multiply everything in row 2 by negative 1. Which is going to give us 0, 1. But the other side is going to be negative 1, 2. Telling us that A inverse is the matrix 5, negative 9, negative 1, 2. There it is. Question on any of this here? Imagine doing this with a 3 by 3. Now, thinking about matrices in these here, well, let's think, actually, before we do that, let's think about functions. Did every function, when we were given two functions, or any function, did they always have an inverse? Well, no, because if they didn't pass the horizontal line test, their inverse wasn't a function. It didn't work. We could find it, but it technically wasn't a function. So, thinking about that there, do we think every matrix will have an inverse? No. So doing this here, there's sometimes we can try to do this as much as we can, but there's no way to get this here on the left-hand side. That would be quite frustrating to sit here and manipulate it and try and try and try and then figure out, well, there is no inverse. There's no way to do this. So before we move on to the next one, I'm going to erase all this here. We have this. And it is not on your paper. I think there might be a little mark on the page somewhere where it's just discolored, or maybe the printer just didn't even show it up. I would put this down. A inverse is equal to 1 over AD minus BC times the matrix D, negative B, negative CA. And really this is saying works if A is the matrix A, B, C, D. Now, before we go into the next matrix or finding the inverse, I'm going to do this formula with this one here. So the first part of this formula is 1 over AD minus BC. So AD, these two here, in our case would be 2, 5. So we'd say 2 times 5 minus BC. 2 going the other direction, which would be 9 and 1. Multiply those together. Times the matrix. In the matrix, if we notice, A and D switch places. So for us here, 2 and 5 are going to switch. So 5 is in the top corner, 2 is in the bottom. B and C change signs. So that would be negative 9 and negative 1. Well, that matrix already does look like the inverse, doesn't it? And we'll see why here in a second. Because if we do this first part, well, 2 times 5 is 10, minus 9 times 1 is 9. Well, 10 minus 9 is 1. Well, 1 over 1 is just the same thing as just 1. And anything times 1, so we're just saying that I have 5, 9. that's
Josh Kramer, come to the office. Josh, come to the office.
Questions on this here. Now, there's not a nice formula that I know of or found, well, I also haven't looked, to find the inverse of a 3 by 3. There's not a good way to find it. Now, one thing that we have covered, because I think...
May I have your attention, please? If you brought finger foods for the cafeteria staff party, would you please bring them to the library? Thank you.
Now, one thing to know for sure if a matrix C has its inverse is this part here, AD minus BC cannot equal 0. Because if this product here, or if this here equals 0, then it's not invertible. It doesn't have an inverse. Now, we haven't covered it yet specifically in here, but I think everybody has covered this, because if you've had Algebra 2 covered matrices, we've talked about this before. This here is the determinant of A. The determinant of a 2 by 2 is this here. So if the determinant is 0, it is not invertible. It does not have an inverse. And that's true for a 3 by 3, any matrice. If the determinant of that matrice is 0, it's not invertible. It doesn't have an inverse. Now, we've already computed as a result of example 3, and what they're saying there is that formula. And we are pretty much saying that is probably the easiest way to find an inverse, yes, especially compared to that. Because 2 by 2 was it 2, 9, 1, 5. That's what I thought, but wanted to make sure. So I typed it in. So second matrix over to math, because as we kind of covered this before, all the stuff that we can do with matrices, all the operations the calculator can do, are normally here. So the first one we have is determinant. I've not looked into what the little t is. DIM, I find this kind of an interesting one to have because it stands for dimensions. So to see what the dimensions of the matrix are, you have to put it in. So if you wanted to know what the dimensions are, you can do that. Yeah, double checking. One of the ones that I think this would be helpful with is multiplication, to see if they would work, and it would tell you what the new dimensions would be. If you didn't remember the trick, that the new dimensions of any multiplication that does work is the rows of the first, columns of the second, it would tell us that there. Otherwise, you had to put the dimensions in to make the matrix. Now it's just going to tell you what they back are. Fill, identity, random in, augmented, matrix list, list matrix, unit sum, reduced or row epsilon form, reduced row epsilon form, row swap, row plus, row times, row plus. Well, none of those were inverse. But how did we write an inverse? A to the negative 1, yes? Well, matrix A. I do have a negative 1 button, yes? So we have 5, negative 9, negative 1, 2. Is what it told us the matrix was. And according to the formula, if we typed it in, 1 over AD minus BC times the matrix, where we switch A and D, and switched and made B and C both negative. This is the exact same one. We end up getting it, and we've already seen that this is this one here indeed.
So, every probable they flip it.
The first and second one, yes.
And the other ones become negative.
Yes. Now, Yeah, and it works out that way every single time. Now, will they always work out that I'm going to get a highlighter. Well, I'm going to get a highlighter out just in case y'all come back and watch it, so I'm not just pointing. That these two will always be negative every single time because we're multiplying it by this here. Now, if this fraction works out to be a negative, when I multiply it with this here, well, this is now going to be negative. This one's now going to be positive, positive, negative. So sometimes they won't look like the exact same numbers because of that fraction, either being a fraction or an integer might change how it looks. Now, we did have a matrix plugged in for B, so we can take B inverse. Is this here? So 3, 2, 7, 5. So this one here, none of them are negative, but I believe for matrix B, well, second matrix B, try it again, B, 2 and 7 were already negative, so they became positive. 3 and 5 switched. And if we look at the product, minus negative 2 times negative 7, we get 1 again, so it's not affecting it. Does that make sense? Any questions on any of these here? Yeah. Show that matrix A is singular. Well, that we can take an inverse. So let's go on and type it in and let the calculator do this for us. If one of y'all will read it. Yeah, so I'm not flipping back and forth. Where are we at? 1? 1.
2, 0, 4, 5, 1, 2, 1, 1.
I wasn't that bad. So I can quit. Now, we can do the same thing, or if I'm being lazy, I can scroll back up, hit A inverse. So singular means it does not work. You know, now again, we said the determinant of this would be 0. And if the determinant is 0, we cannot have an inverse. So, and we haven't quite gone over determinant, so I'm going to show you how we can do this in a calculator. Determinant, second matrix A, is 0. If the determinant is 0, it does not have an inverse. It does not exist. So if it does give you an error and you're doing this here, well, it's because the determinant of A is 0. Can't have an inverse. And we haven't gone over determinants in here yet. We've done them in Algebra 2. We'll go over those tomorrow. Find the inverse of A if possible. Well, I don't think we need to see another one. I'm not going to make y'all do these by hand, going through the row operations to determine this. But I think we feel good with these here, yes? Use the inverse coefficients to solve the matrix. Now, what we do to do this here, because we'll do A times X is equal to B. Now, with matrices, we can't divide. There's no way to divide matrices. So if we were to solve this here, AX equals B, and it was not matrices, well, we would divide both sides by A, and we would get our solution. Now, what we do to solve this is use inverses. Because we know A inverse times matrix A times X equals, we'll apply to both sides, because A inverse times A matrix times its inverse, is the identity, which is essentially 1. Which will give us A inverse times B. how we do this and what everything stands for is, one, we rewrite the left side, so the x, y, and z, as a augmented matrix. So for the first row, we'd have 1 for x, 3 for y, and since there is no z, it is 0. Second row, 1 for x, 1 for y, negative 2 for z. And the last row, negative 3 for x, negative 3 for y, 5 for z. Now the question is, why don't we do the little bar or include negative 10, negative 4, negative 11 in the first, second, and third row respectively? Well, with inverses, we just take the numbers in front of x, y, and z. Now what this is being multiplied, because this is our a in the example that we had. Now our x in the example is going to be a column matrix of the variables in order, x, y, z is equal to. And the b, in our case, is the numbers that it's equal to. So negative 10, negative 4, and 11. Now, if we multiply A's inverse by this matrix B, we will get the solution. So that first main step is going to be to find the inverse. Well, I'm going to just use the calculator. Say second matrix, edit, 3 by 3. Because I think it's 1, 1, 0, 1, 3, 0. There we go. And then we go 1, 1, negative 2. Thank you. I made that go a little bit faster. Second quit. Second matrix. Edit. Well, nope. Went back to matrix A because we want matrix B this time. And this is going to be A 3 by 1. I want to say negative 10 is the first number. And we can double check. 11, yes. So we have the two matrices plugged in, yes? Now we don't want to do matrix A times matrix B. We want what? A inverse. So I can go matrix A inverse second matrix B, because that's what we said. Our x, y, z, our 3 by 1 matrix with our variables is equal to A inverse times B. Enter. So that's telling us that the matrix x, y, z is equal to 2, negative 4, 1. So as a point, it would be 2, negative 4, 1. Or we're saying that x is 2, y is negative 4, and z is 1. Questions on any of this here? Negative 10, negative 4, negative 1. No, other way. No. So negative 10, negative 4, 11. So if we type the whole thing in like this here, because we've done this before, I'm going to go second quit. This time I'm going to say second matrix RREF, second matrix A. Still get the same thing. It's just another way to solve it. Does that make sense? So we can solve it using inverses. We can solve it with reduced row epsilon form. Either way works. And that's it. Excuse me.